Hello students. I am Sachin Vivahare, your maths teacher. Uh, We already started the shortcut methods to find out particular solution of the linear differential equation. In previous session, um, we completed a shortcut method to find out the particular solution of exponential function. Then we completed trigonometric function and hyperbolic function. Now we are going to see here the case 4 when the RHS of the function is algebraic function. Okay, so whenever the RHS of the function is algebraic function, it is in the form like here 3x square minus 5x plus 2. That means it may be in the polynomial form or sometimes only x raised to n. It may be x cube, x square, anything. Okay, so if RHS is algebraic function, how to find a particular solution? Yes, the step one is common. We are going to see here the example. By example, we'll see the method. So the question is here, solve d cube minus 2d plus 4 of y is equal to 3x square minus 5x plus 2. Step 1 is not new to you. Yes, I know all of you can do it. First, we considered the auxiliary equation here. The auxiliary equation is a d cube minus 2d plus 4 is equal to 0. We calculated the roots by using a calculator method that we already discussed while finding the complementary function, and we get the root minus 2 and plus or minus I. Okay, there is alternative way also. Those who are not interested to use a calculator, remember, for a cubic equation there is always at least one real root, and that real root have the opposite sign that of the constant term. In this case, constant term have the sign plus 4. So yes, that real root will have the opposite sign. Here you can observe that is a minus. And that is again a factor of that constant term. So factor of the 4 means 4 is a divisible by 1, 2 and 4 itself. So minus 1, minus 2, minus 4 can be the root, and you can check it by hit and trial method. And once we get that minus 2 by hit and trial method, then you can find out the pair of complex root. But that is a lengthy way, so better you can use the calculator. And once you get this root, yes, we know c1 e raised to alpha x, okay, or c1 e raised to m1 x plus e raised to alpha x c2 cos beta x plus c3 sin beta x is our complementary function. Okay, so this part we already discussed in the detail in complementary function. The new part is here, step 2. In the step 2, yes, we have to find out yp, and this is the standard formula for particular solution, 1 upon pi d of fx. Okay, so just we replace pi d here, that is 1 upon, this is a pi d, d cube minus 2d plus 4 of fx. The fx is the RHS of the given differential equation. So this is 1 upon pi d. Okay, so that about just a replacement. So the method is yes, we have to remove the operator 1 by phi d, and to remove this operator, always we have to take the lowest degree term in the function of phi d, in this pi of d. Now, if you observe in pi of d, d cube is a third degree term, minus 2d is a linear, and 4 is a constant, that is the lowest degree term with a degree 0. So we have taken 4 as a common. Okay, we have taken that 4 as a common from the denominator because that lowest degree term is 4. Once we take 4 as a common, the remaining part is converted in the form of either 1 upon 1 plus t or 1 upon 1 minus t. You can observe in this case it comes in the form of 1 divided by this 1 plus, and this bracket you can consider as a t. Okay, and we have that formula, 1 upon 1 plus t is equal to 1 minus t plus t square minus t cube plus t4 and so on. So this is the infinite series. So where to stop? A simple thing that you can remember: if we have quadratic equation, expand that up to the quadratic term. If it is cubic polynomial, expand it is up to bracket cube. Okay, that way. So in this case, we have given a polynomial of degree 2 that is a 3x square minus 5x plus 2. So we have taken that 1 upon 1 plus t as this is 1 minus t plus t square only. Okay, plus t square only because it is of degree 2, 3x square. So when we return that 1 minus t plus t square in the bracket here, this is 1 minus t is this entire bracket, t square, this is bracket square. Okay, so that's one. Many of the terms again we have to ignore it because if this is the quadratic equation, its third derivative or yes, we can say third and the higher order derivatives are zero. Okay, because as it is a quadratic, the maximum second derivative will exist. So we can ignore the terms of d cube, d raised to 4 and so on. So what I done here, this one is written as it is, first one. This one is taken as it is here, 1. Then this d cube term, this is a 0, ignored because the third derivative of that 3x square is a 0, so ignored. So we left with minus 2d upon 4 and the outside bracket minus sign, that minus minus become plus 2d by 4. Okay, so from this term only this term appeared here as it is. Okay, that is a 2d by 4. Next, from this bracket, now we have to see here is the this bracket, d cube minus 2d upon 4 bracket square. Again, if you observe, this is like d cube by 4 minus d by 2 bracket square. Or okay, so in bracket square it is like a square minus 2ab plus b square. So first term is a d raised to 6. Yes, no, not written. Middle term that become minus 2d raised to 4, not written. Only the last term, which is a minus 2d by 4 bracket square, is here, which is a 4d square by 16. Why it is written? Because its a degree is 2, up to 2. So other terms like d raised to 6 or d cube or d4, that not required, so ignore it. So only the required term, because even though you write that term of d cube or d raised to 4, later on when you differentiate it going to the 0. So unnecessary unwanted terms, no need to write it. And this that fx on the RHS still as it is, nothing we done with that. Okay, now we simplified again the bracket. The simplification of this bracket is 1 plus d by 2 plus d square by 4 of that fx. Okay, now the last step, the simple thing that we left. So when we apply this one on this bracket, the bracket remains as it is. Okay, this is 1 into that bracket. Next, d by 2, of that bracket, d by 2 of the bracket is here. Okay, this is d by 2. And then lastly, this d square by 4, is written here, which is a second derivative of the bracket. Okay, so obviously the first derivative is a 6x minus 5, second derivative is a we'll say 6x, sorry, only 6 there. Okay, that's the second derivative and that's written there. And remaining thing is a simple simplification, and at the end we are written here yc plus yp as a complete solution. So that about solving the differential equation when the RHS is an algebraic function. Okay, so thank you. We'll stop here. Hello, I am Sachin Vivare. Let we see the method to find a particular solution of algebraic function. In algebraic function, we'll see this thing with the help of example. The example is here: d2y by dx square, minus dy by dx plus y is equal to x cube minus 3x square plus 1. Yes, step 1 is a common yc. Auxiliary equation, d square minus d plus 1 equal to 0. Roots are in complex form, which is alpha plus or minus I beta. Sorry. So yc is e raised to alpha x, that is e raised to alpha is in this case minus 1 by 2 and beta is a root 3 by 2. So e raised to minus x by 2 c1 cos root 3 by 2x plus c2 sine root 3 by 2x. That about yc. Step 2 is important. Step 2 is a yp. This is the standard formula 1 upon pi d of fx. In this case, our fx is algebraic function, which is a x cube minus 3x square plus 1, and the function of d is a d square minus d plus 1. Okay. The method for algebraic function, yes, we have to take the lowest degree term, and here again, if you observe, the d square have the degree as a 2, minus d that have a degree as a 1, and 1 is a constant term which have the lowest degree as a 0. So just we taken 1 as a common, so nothing is that. Just rearrange the term then. If we take 1 as 1 plus d square minus d, so again it is written in the form of 1 upon 1 plus t, and we have that formula for 1 upon 1 plus t is 1 minus t plus t square minus t cube, and so on. So in this case, if you observe, the maximum degree that exists is a cubic, that is x cube. So we have to write this bracket as a 1 minus t plus t square minus t cube. So up to t cube, the reason is here is x cube. Okay, that is the simple thing that you have. But yes, we are going to ignore few of the terms which are not required later on. So first of all, the simplification is written 1, this bracket minus this is written somewhere here. Now in this bracket square, d raised to 4 is written. Middle term is a minus 2d cube. Last term is a d square. So that are the three terms written for that d square minus d bracket square. But for this last thing, okay, for this last thing, only one term is taken. The reason is all other terms, if you observe the first term, d square bracket cube, that is a d raised to 6, not required because 6 the derivative of this third degree polynomial is a 0. Middle term, like we know that a minus b bracket cube is a cube minus 3a square b plus 3ab square minus b cube. So that minus 3a square b or minus 3ab square, that are again the higher derivatives like d raised to 4, d raised to 5, that are again 0. So only minus b cube is left, and that is here minus d cube. So that about the last term is written. Okay, the further simplification gives us only these three terms because minus d square plus d square gets cancelled. D raised to 4 is itself a 0. Fourth derivative of that bracket is a 0. No need to write it. Plus d as it is here, and here is a minus 2d cube plus d cube, and that become only minus d cube. And then here 1 into the bracket, derivative of the bracket, and third derivative of the bracket is written. So this is 1 into bracket, first derivative of the bracket, and third derivative of the bracket is written, and this is the simplified term. So at the end we just written yc plus yp as a complete solution. And that about second example for you about algebraic function. Okay, so hello, I'm Sachin Vivare. This is the third example on the algebraic function. So here the is uh, example is d cube, sorry, d square minus 9 of y is equal to x cube. Okay, d square minus 9 of y is equal to x cube. So step 1 is uh, complementary function. For complementary function, yes, we equate d square minus 9 is equal to 0. We get the root as a plus or minus 3, and we get yc, which is a complementary function, as a c1 e raised to 3x plus c2 e raised to minus 3x. That about a complementary solution. Now for particular integral, 1 upon 5d of x cube, and in this case the lowest degree term is a minus 9. So minus 9 is a taken common. We left it with 1 minus d square minus 9 of x cube. Now in this case, yes, we come across a small different thing, which is 1 upon 1 minus t. 1 upon 1 minus t is nothing but it is 1 plus t square plus t cube plus so on. So all terms are positive here. If you observe, 1 upon 1 minus t, 1 plus t square plus t cube and so on. But 1 upon 1 plus t, in previous examples we've seen, it is 1 minus t plus t square. So alternate plus minus sign is there. So this is 1 upon 1 minus t, and here is the expansion 1 plus t square. Actually, this writing this t square is also not required because t square of means second t square of d square by 9, that become d raised to 4, and the fourth derivative of x cube is a 0. Fourth derivative of x cube is 0. If you ignore that at this stage, if you write only these two terms, that is also correct. Okay, no need to write that fourth term. So you can write only two term, 1 plus d square by 9, because the next is plus d square by 9 bracket square, that is actually the 0. So only these two will exist. This is obviously the 0, fourth derivative of x cube. So x cube is as it is. This x cube is as it is here. second derivative of x cube. Second derivative of x cube is 6x written, and we got this as a yc, and at the end sorry, that is yp, and at the end we written yc plus yp as a complete solution. So thank you. That's for today. So three examples I given on algebraic function. Yes, in next type, when we see the combinations now, the combination of exponential and algebraic or trigonometry into algebraic. So that time again we have to come across this method. So more examples we'll see in the next type again. So thank you. That's for today. Hi everyone. I am Sachin Vivahare. We already seen the methods for finding the particular solution of exponential function, trigonometric function, hyperbolic function, and algebraic function. Now we have the combination of these four only. So the first combination is that is we have uh, e raised to x, e raised to x into v. So this is the first combination, exponential function into any other function. So v can be a trigonometric, hyperbolic, or algebraic. So whenever we come across in the RHS e raised to x into any other function, okay, then the simple thing is that first we'll take exponential function outside the operator by replacing d by d plus a. Exponential function come out. So you can observe some here how it is given. So whenever there is a 1 upon phi d of e raised to x into v, e raised to x is written outside here, outside the operator, and then phi of d is converted as a phi of d plus a. And then depending on v, if v is a trigonometric function, replace d square by minus a square. If d is a hyperbolic function, replace d square by plus a square. And suppose v is an algebraic function, then convert it in the form of 1 upon 1 plus t or 1 upon 1 minus t form by taking lowest degree term as a common. Okay, so that is just like all previous method. So only the first extra thing that we have to take exponential function outside the operator by replacing d by d plus a. So that about a method. Now we'll see one or two examples probably the example 12 and the example 16 as a solved example. Yes, remaining examples you can practice yourself. Okay, so thank you for this video. Welcome in the second video of the type e raised to x into v. So here we are going to see the first example on the form e raised to x into v. You can observe the RHS mainly. This RHS is like e raised to 2x into x square. So it is in the form of e raised to x into algebraic function. Okay. So entire equation that we are given is a d square minus 4d plus 3 of y is equal to x square e raised to 2x. Okay, so in exercise that is x cube there, but here we are considering for x square. Okay, so right now the step one is yc. That's not new to you. I think everyone can do it. So yc, you will get c1 e raised to x plus c2 e raised to 3x for a distinct root. Okay. Now, the step 2 is the new for us, which is 1 upon pi d of fx. In this case, pi d is 1 upon d square minus 4d plus 3 of x square into e raised to 2x. So, as it is in the form of e raised to x into v form, so the method is replace d by d plus a. In this case, a is a 2. So, here we replace d by d plus 2. Okay, we are replacing d by d plus 2. Now, when we replace d by d plus 2, this e raised to 2x, we are writing outside the operator. This is also an important thing. Many of the time you forget to write that is outside the operator. Don't keep it here again. So that is not correct. Okay, so definitely you should not write somewhere here. So you can take it at outside. You should keep it outside, and then we replace d by d plus 2. So now throughout till end, so that e raised to 2x is outside as it is, no change there. Only we are simplifying uh, this expression. So the square of d plus 2 is a d square plus 4d plus 4 minus 4d minus 8 plus 3. The simplification gives us d square minus 1 only. As it is algebraic form and we have 1 upon phi d. So the method is we have to convert this in either in the form of 1 upon 1 plus t or minus t. So in this case, it is coming as 1 upon 1 minus t. So 1 upon 1 minus t is written as 1 plus t square. Actually, this term is also not required because d raised to 4 of x square is 0. Okay, so that's a 0. So only these two terms are important. So 1 upon 1 minus t is 1 plus t square only. That's one required. And now x square into 1 is x square here. D square of x square is 2. Second derivative of x square is 2. And at the end, yc plus yp is the complete solution. That about our first example. Okay, so thank you. Hello everyone. Let me start a second example of the type e raised to x into v. The example is now d square minus 3d square plus 3d minus 1 of y is equal to root x into e raised to x. Okay, number one is a complementary function that everyone knows. So here it is a perfect cube of d minus 1. So it is a d minus 1 bracket cube is equal to 0. So 1 is repeated thrice. So the yc will be c1 plus c2x plus c3x square into e raised to x. Now in the step 2, the formula is yp is equal to 1 upon pi d of fx. I observed that many of you are writing this as either fx upon pi of d, or some of you are writing fx first and then 1 upon pi d. So remember, these things are totally wrong. These are not correct ways of writing. So keep operator first and after that you write fx. Once you write fx before the operator, the meaning is that already you operated that operator on that function. So try to keep the function outside the operator as it is. Here our function is root x into e raised to x, and our method is whenever e raised to x into v is there, we replace d by d plus a. In this case, we replace d by d plus 1. So this is our method that we have. Now when we replace d by d plus 1, actually this exponential function, we operated that operator on that exponential function. So exponential function come before the operator. Now that operator is operated on exponential function, and because of that we replace d by d plus 1. And now if you observe here, we replace d by d plus 1 and we return exponential function before the operator, and root x left as it is. The simplification of that bracket, this is only remain 1 by d cube. Now 1 by d cube, remember 1 by d is this 1 by d is an integral operator. So as 1 by d is an integral operator, so we have to integrate this root x 3 times. Okay, root x 3 times. So first integration of root x means x raised to 1 by 2, and we have the formula for x raised to 1 by 2 as x raised to 1 by 2 plus 1 upon 1 by 2 plus 1. So that is x raised to 3 by 2 upon 3 by 2. Okay, so that is the first integration. Second integration become x raised to 5 by 2 upon 5 by 2 into 3 by 2, and third time integration becomes this one. So the simplification gives us 8 upon 105 into e raised to x into x raised to 7 by 2. And don't forget at the end to write that yc plus yp as a complete solution. So that's for today. So tomorrow we'll see the new method. Okay, so we'll stop here. Thank you. Hi everyone. I am Sachin Vivare. We are in the sixth shortcut method of finding a particular solution. Sixth method is x into v. Okay, so whenever RHS of the differential equation is in the form of x into v, how to find the particular integral? The formula for getting particular integral in that case is this one. It is a little lengthy formula, but yes, the task what is happening here, that is x into v is the given, and x will come out by the formula x minus x minus phi dash d upon phi d into 1 upon phi d of v. So x is taken out from the operator by this formula. So we are not going in the derivation of any of the formula right now. Just learn the formulas and let we use, or let we apply that to get the required particular integral. One more important thing, last 3 years there is not a single question on this type. Majority of the examples which are coming for the 10 marks, they are coming on the method 1 sorry, I wrongly mentioned the 10 marks. It is for 5 marks which are coming on first 5 methods. The method number 1 to method number 5, that is mainly comes for the 5 marks. Yes, 6 method not asked in the last 3 years. Okay, so we'll see one or two examples on it. Okay, so that's for the theory. So I'll stop here for the theory. Okay, so we'll start the first example. First example of the form x into v. If you see the example that we have here, d square minus 4 of y is equal to x into sine hyperbolic x. Okay, x into sine hyperbolic x. So step 1 is a common. So where the auxiliary equation is d square minus 4 equal to 0. So the roots are plus or minus 2. C1 e raised to 2x plus C2 e raised to minus 2x is the yc. That is a complementary function. Now the step 2. For yp, that we have 1 upon pi d of fx. 1 upon pi d is written here. 1 upon pi d of fx. Fx is x into sine hyperbolic x. As it is in the form of x into v, the formula is here x minus pi dash d x minus pi dash d upon pi of d into 1 upon pi d of sine hyperbolic x. So you can observe this x is coming out from the operator. So this x is coming outside the operator. Okay. Now, yes, depending on that v now. So in this case, v is a hyperbolic function. So the method says replace d square by a square. Okay. So if it is a trigonometry, we replace d square by minus a square. If it is say uh, exponential, we replace d by a. Okay, so one example can be solved by more than one method. For example, if you have x into e raised to ax form, so in that case you can use this formula, which is x minus pi dash d upon pi d into 1 upon pi d of e raised to ax, or you can use that e raised to ax into v form. So both way you are getting the same answer. Okay, so go by any of the method, answer should be same. So let me come to this example again. So pi d is in this case d square minus 4. So pi dash d become 2d. This is a phi d and this is again 1 upon pi d. So just we are replacing d square by plus 1. So both we have to replace d square by plus 1 here as well as here also. So that replacement we done in the next step here. So yes, you can replace d square by plus a square at both the place. After that, yes, this is the simplified form. 2 by 3 of d means we have to take a derivative of sine hyperbolic x, and you should know the derivative of hyperbolic now. The derivative of sine hyperbolic x is a cos hyperbolic x. Okay, so in this case that only we require. So the final answer you can see at the end, which is written here. Okay, so the main thing is that yes, the formula. Yes, you can remember the formula x minus pi dash d upon pi d into 1 upon pi d of v. Okay, so that about your first example. Thank you. Okay, welcome in the second example of x into v form. So here, uh, the example I am taken as is d square minus 2d plus 1 of y is equal to x into e raised to x into sine x. So it is a combination of three functions. One is algebraic, second is exponential, and third is a trigonometric. Okay, so yes, we can go one by one. We'll see it here. So first of all, the roots of auxiliary equation, that is one repeated. So we have the yc as a c1 plus c2x e raised to x, because one is a repeated real root. Okay, now the step 2, that is yp is equal to 1 upon pi d of fx. Okay, remember, just like a Laplace transform, in the Laplace transform we already seen, yes, we have to keep that shifting at the end, but here we should take that e raised to ax first outside. Okay, sorry. So Laplace is a different. In the Laplace we keep exponential at the end, but here first always take out exponential outside first by replacing d by d plus 1. Here we replace d by d plus 1. Okay, so that exponential function come outside the operator. This is outside the operator, and we replace d by d plus 1. So we left with 1 upon d square. Now 1 upon d square of x sine x we left. Now there are again two ways. One of the way is, we know 1 by d is an integration operator, so just integrate x sine x two times. Okay, so integration of x sine x first time and one more time. So that is one of the way. The second way is the formula, which is x minus pi dash d upon phi of d into 1 upon pi d of sin x. So that is the second way. So in this example, phi of d is a d square. So pi dash d is a 2d. This is a pi d. So we replace d square by minus a square. So we replace d square by minus 1. In this case, yes, you can replace minus 1 here also, but that time you have to differentiate sin x. Okay, you have to differentiate sin x. But right now I cancelled that one of the d, and so it left 1 by d only. And this is 1 by d is the integration of sin x, integration of sin x. So that is a return. This is 1 by d sin x. Integration of sin x is a minus cos x. So minus minus plus. And don't forget to write at the end that yc plus yp as a complete solution. So that about the second example of